Hi guys, let's do all nodes distance k in binary tree. So we're given the root of a binary tree, the value of a target node called target, and an integer k, and they want us to return an array of the values of all nodes that have a distance k from the target node, and they say we can return the answer in any order. So given in example 1 where we're given this tree and target equals 5, k equals 2, then starting from the target node 5, if we go a distance of 2 away from this node, then all of the nodes of that distance would be 7, 4, and 1, because each of these are 2 away. So like for 7, we would be like this would be 1, 2, 1, 2, 1, 2, right? So those are all a distance of 2 away. And so we would return 7, 4, 1 as a list. So in example 2, if we're given just this singular node of 1, then we would return an empty list because k is 3 and there's no nodes that are a distance of 3 away from this node because this is the only node. So basically, we have a little bit of a problem here, right? Because if you guys remember, in a tree, we can only traverse using node.left or node.right, and that will bring us to the left or right child node of this parent node. But in this problem, we might need to traverse down, right? Except for like in 7 and 4, we would traverse down, and that's no problem. But for like to get to 1 from 5, we would need to traverse up, and you can't possibly do that in a tree. So to get around that, we're going to have to convert this tree into a graph so that we can basically have undirected edges that will go either way, and then we can traverse backwards basically. And then from that graph, like once we build the graph, then we'll start a BFS from this target node of 5 basically, and we can just traverse the BFS a k number of times. So if k is 2 in this case, we can just traverse the BFS twice, and then the current like level that we're at will contain all of these nodes, and that's what we can just return. So that should be pretty straightforward. But first thing we're going to do is build out that graph. So we're going to use a hash map to represent that, and it's going to map the node to all of its neighbors. So to a list of nodes. And then we're going to just have a separate method to build out the graph just so it's a little bit cleaner, but I'll just call that method here. So we're going to pass in the root because that's our current node that we're starting at, which in this case is 3. And we will need to pass in, so to build out the graph, right, all of its neighbors, were basically the neighbors of a certain node is itself, its children, which is node.left and node.right. Well, I guess not itself, but node.left, node.right, and the parent node. So like from 5, right, node.left is 6, which is a neighbor. Node.right gives us 2, which is a neighbor. And then we also need the parent, which is 3, which would be a neighbor of 5 as well, if we think of this like a graph, right? So we're going to need to pass in the parent, which for the root node is going to be null because there's no parent. And then we're going to pass in our graph because we're building out this graph, so we're going to need to add them in as we go. So let's start this method. So private void build graph. We're passing in the node, the parent, and the graph. So tree node. Okay, and then our base case, if our node is null, then we can just return because there's no work to be done anymore. Like if we reach the bottom of the tree and then we get to like 4's node.left or node.right, and then these are null because there's nothing there, then we would just return. So if node is null, return. Okay, and then if it's not null, then we will build out an edge from the node to, so like our graph starts out as empty, right? We need to add our current node as a key in the graph. So if we don't already have it, so graph.put if absent, node and an empty list. So if we're starting at 3, because we passed in 3 as the root here, then we don't have 3, so we'll put 3 with an empty list, like that. Okay, and then we need to check if the parent is null, because if the parent's null, then we can't actually do anything here, because like we're mapping it to its neighbors, right? And so we can't actually map the parent as a neighbor if there's no parent. So we're gonna check if it's null. If it's not null, then we will actually map them to each other. But so if it's not null, then we'll map them to each other in the graph as neighbors. So graph.getNode.add parent and .getParent.add node. And we're adding it both ways because it should be like an undirected graph. But in this case, we don't have a parent, so we skip over this. And then we're just going to do the same thing for the left child and the right child. Okay, so then in the next iteration, we're calling 5 and 1, and then that will call 6 and 2, and right will call 0 and 8, and then 2 will call 7 and 4. So basically, then we will, like in the end, our graph is going to map 3 to 5 and 1, 5 to 6, 2 and 3. Oopsie. One to 3, 0 and 8. 6 to 5, 2 to 7, 4 and 5, 0 to 1, 8 to 1. I think that should be it. Let me double check I didn't miss anything. So 3, 5, 1, 6, 2, I missed 7 and 4. Okay, so 7 will be mapped to 2. Oops, why do I keep doing that? 4 will be mapped to 2. Okay, I think that should be it now. Okay, so now that we've built out our graph, then we can actually start our BFS from this target node, because we can go both ways now. So we're going to need our queue for our BFS, so we're going to add tree nodes into the queue. And we're going to need a set to keep track of our visited nodes. So visited. Okay, and then we're going to add our target into both of these because that's where we're starting at. So queue.add target and visited.add target. So now our queue should look like, if we go off of example 1, it will store 5, and visited will store 5 as well, because we just added them both. Okay, and then we need to, we're in our BFS, we are traversing k number of times, so we need a variable to keep track of how many times we have traversed the BFS so far, or like how many levels in we are, basically. So we're going to say int distance is 0. We're going to start it at 0, and we're going to increment it every level. That way we know we can stop once we've reached k. Okay? And then while our queue is not empty, then we will continue to do our BFS. So int nodes in level, in current level is 0. And actually, okay, so if our distance is k, then we'll just break out of this loop. So if distance is k, then break. Okay, and then we're gonna continue our BFS here. So nodes in current level is 0. wait, why did I say 0? Q.size, sorry. I don't know what's wrong with me today, guys. So, okay, and then we're gonna need to loop through all of the nodes in that current levels, yeah, so we're, okay, so if we have, like, let's say 6, 2, and 3, we're gonna need to loop through each of these nodes, and then we're gonna need to check all of their neighbors as well, like, to add into the queue for the next round. So for, oops, like I said, guys, I don't know what's going on. Okay, in current level, I++. So this is going through the nodes in our level right now, which currently is just 5. As you can see here, we just have 5. But then we're going to remove it. So our node is q.remove. So that's 5, and then we remove 5 out of the queue. And then we need to go through 5's neighbors to add those into the queue for our next level as well. So for each neighbor in graph.getNode, which will be this list here for our current node 5, then we will check if we've already seen that node, or .contains neighbor. Then we will add it to the queue and to visited. So visited.add neighbor, queue.add neighbor. Okay, so for every node in here, so 6, we don't have that in visited, or so we add that to both. So 6. Then 2, we don't have a 2, so we will add that to both. 3, we don't have a 3, so we add that to both. Okay, and then we exit this loop. And then once we have done that, and we are out of this loop as well, because nodes in current level, was 1, because we only had 1 node in our current level, which was 5. So we're out of this loop as well. And then at the bottom, then we need to increment our distance variable, because for our next iteration, or like, we've completed this level, so like we're at the next iteration, which would be a distance of 1 away, right? Which would be 6, 2, and 3, which, as we can see here, 6, 2, and 3 is next in our queue. So basically that's how that works. We can do another iteration, I guess, to see how this works. So next iteration, nodes in current level is 3. So we'll loop through 3 times. Oh, first of all, well, distance is not k, because distance is 1 right now, because we started at 0 and we incremented it once. So it's not k, because k is 2. So we don't break, we continue. And then nodes in current level is 3. We have 3 nodes in the queue. And then we remove the top one off of the queue, which is 6. Then for every neighbor in 6, which is this, that's all of the neighbors, we will check if we have it in visited, and we already do, so we actually just skip over it because we already have 5 in our visited set. So we skip over this, and then now I is 1 because it started at 0. Then we remove the top one, which is 2. And then for every neighbor in 2, which is this list, then we will check if it's in visited already. So 7, we do not have 7, so we'll add that to both. Um, 4, we don't have 4, so we'll add that to both. And 5, we already have 5, so we will not add that to anything. And then we will exit this loop, and then this becomes 2, and this will become 3, because we'll take 3 off of the top of our queue. And then for every neighbor in 3, which is just 5 and 1, we will loop through. So if visited contains 5, and it already does, so we skip this statement. Then for the next neighbor, which is 1, we don't have 1, so we'll add 1 to both. And then now we are done with all the neighbors, and then I becomes 3, so we exit this loop because it needed to be at less than 3, as we can see. And then distance will increment, so now distance is 2, and then if we check right now, every node that's a distance of 2 away from k, so that would be 7, 4, and 1, and as we can see in our queue here, we have 7, 4, and 1. So far we're doing good. Okay, why don't we just finish it off because we're almost there. So distance is now 2, which is the current distance actually. So we will break out of this and we don't even bother with any of this stuff. So that's not needed. And then we are done iterating. Now we just need to find a way to return this as a list format because they want it as a list. So we're going to need to initialize a list to store the result and return it, right? And then basically we're just going to loop through this queue and add all of the nodes into the list, or all the nodes values, sorry. So while our queue is not empty, we'll just keep removing things off of the queue and adding them into the list. So result.add queue.remove.value, because we need the value, not the actual node. And then we will return the result. And they said we can return it in any order, so it doesn't really matter how we do this, right? Because depending on how you did all of the previous steps, like this might be in a different order, but it doesn't really matter. And yeah, that's basically it. So let's check that. Oops. Oh god. Okay. Alright. I guess the video can't be complete without a typo. Okay, let's go. Oops. Why am I... Jeez, okay. Time complexity. Okay, let's think about the time complexity here. So we originally, in our algorithm, built the graph by traversing from the root of the tree and visiting every node once to add to our graph. Then once we had the graph, we started from the target node, visited, well, we didn't actually visit every node, but worst case we could visit every node if if k is the same as the number of levels in the tree, or even more than the levels in the tree. Then we'll visit every node again. And I think that's basically it for the time. So that's O of n for building the graph, and O of n for doing our BFS, which O of n plus O of n will give us O of n, where n is the number of nodes in the tree. Okay, and then our space complexity, so let's think about our space, right? So we have a couple data structures going on here, so more than a couple. We have the graph, which is a map, which maps every node to every node's neighbor, which worst case will, well, not even worst case, I guess it's just O of n, because like we could have something like this, which is what we currently have, but like or you could have something like example 2, which would just, the entire graph would, of course the diagram's gone now. Of course, I mean, the graph, will just be the node mapping to nothing. So that will store O of n, because it has no neighbors. Or worst case, like I guess if there's like 3 nodes, then they're all connected or something in a line, then every node will store every other node, still O of n, I think. So I think no matter what, it's just O of n for the graph. The queue, worst case, will store O of n because it's like the number of nodes in every level is how many are in the queue, and like I've said before, a complete graph or tree or whatever will have up to n over 2 nodes in the bottom level, which will just simplify to O of n. And visited will store O of n worst case, because if distance is, I keep saying distance. If k is the distance of like the last level, then like we're storing every single node in the tree or graph in visited, because like we're never actually removing it like we are in the queue. So like it's gonna, like as we can see here, it's getting bigger and bigger every time we traverse or iterate, and then it's gonna eventually store every single node if our k is the last level, or basically every node, because like I guess worst case, the target node could even be the root, and then we actually would store every node. So that's O of n, this is O of n, and this is O of n. So O of n plus O of n plus O of n would give us O of n. Oops. And it's the same thing. So that is it for this problem. Thank you guys for watching, and like and subscribe if you found this helpful. Bye!